So I'm Guido Pupillo from University of Strasbourg. All these logos here just reflect how complicated it is to get funding in Europe. So you have all these kind of different things from France and Europe. Okay, so where are we? So we are in Strasbourg, which is essentially on the border between France and Germany. The tram downstairs goes in Germany, so we are kind of on the border with France and Germany, and we collaborate with a lot of friends and colleagues from all this area and other places in Europe. And we try to make also, kind of pushing certain area of science, including quantum science and technologies, in all this area. This is a priority project there, so there is a lot of stuff to go. If you come to Europe, please stop by. So Strasbourg is a very nice city. Here's one picture. It's very picturesque. It's very nice, full of history. Typically very bloody, actually, history, but also very nice place to be. So, and this is a new center of quantum sciences, where we just moved last year. It's still being built, and this is real. It's not Photoshop, so it's a very nice place. Now, behind this place here, they're now currently building another similar size building, which is going to be connected with new labs, state of the art for quantum optics, etc. So if you don't really have space in Harvard and MIT, please just move to Strasbourg. We have some space. All right, so we're actually building something called ITAMP with Sharon Whitlock in the French and European context. We have an 8-year project to build a dual species system for neutral atom quantum simulators and computing. So stay tuned, but it's an 8-year project, so stay tuned for a long time. You have to stay there. But it's going fine, so it's very interesting. Please come visit. All right, so this is a talk that, the first few slides actually are the same from last year. We met with many people at the Perimeter Institute, and this was just a small subsection of the things that were going on last year, and now they are completely outdated. So before coming here, I was trying to, update this one, so okay, forget about it. So it was here from all the people at this fantastic talks that are going today, tomorrow. In particular, about current gate fidelities, has been smashed by several people. We are still interested in looking at the current limits of fidelities and trying to increase these fidelities and try to go towards quantum error correction. So I'd like to talk about it and that's about it. All right, so this talk is about time optimal gates, which we developed with Sven, who is a PhD student. He's here. Please just go. He's very good. Just don't tell him. And so please get on. So this is time optimal gates and also robust gates, also collaboration with Jeff. And then I would like to spend a few minutes about talking some ideas for multi-qubit gates with neutral atoms coupled to driven cavities. So these are 3 topics we have been working the last year. All right, again, the next 2 slides are just to recap where we were until a few years ago. A few years ago, basically the field was following the original proposal of how to do gates with neutral atoms. We're all familiar with this, so we'll just kind of skip. You need the 2 lasers here to make essentially differential shifts depending on the preparation of the states in some ground, river state, and some intermediate states. Okay, so this was passed by a very nice idea and implementation here I said before, Boston and Cambridge. So here in Cambridge, and this is the idea from this group of wonderful people. And so the idea was to have now a global laser addressing both atoms. We have this, so therefore this simplifies a lot of implementations because you have now symmetric gates, and this makes conceptually a lot of sense. And also experimentally becomes much easier because you don't have to control each atom. So I'm preaching to the Pope, as you will say, so I will not continue on this one, but this basically sets how you do this kind of gate. And what we did, of course, we saw this, we had to start building on our own in Strasbourg something, start thinking about, okay, can you learn from these ideas and do even better in some form by doing faster gates and maybe generalize to higher qubit gates. That's where we were until a couple of years ago. So we'd like to start talking about first the time optimal gates and then robust gates, and then go into various ideas for multi-qubit gates. So the first work we did in this area, so the first ideas was about, okay, to start from, from this idea here of this global global laser addressing symmetrically the two atoms. So we have a three-level system as in the original proposals with two atoms in ground state and excited state, interaction with the Rydberg state, be the double blockade mechanism. And now we have just a single laser with a Rabi frequency that now can be tuned in time. So the idea is, okay, so can we control now this external laser in a form that makes these gates faster and maybe robust with respect to certain kind of noise? So the first thing, of course, you have a Rabi frequency, so you have the amplitude, and you have also the phase can be controlled. Now, the first thing that you want to, if you think about it, if you want to go fast, the better thing you can do is just to crank up your Rabi frequency as much as you can and leave it there. And that's, of course, will be fast. And then the idea is, can you actually now control the phase in order to achieve the gates you want? So how do we do it? We use a series of theory ideas. One is based on optimal control methods, and this is purely numerical. So you can, this has been used in many fields of science, including here for cold atoms. There is a lot of pioneering work from all these people. The idea is to use optimal control methods to improve the speed and fidelity of quantum gates and provide also new solutions for quantum gates. And what we use specifically is something called GRAPE. So gradient ascent pulse engineering is one possible way of doing this. The idea is to optimize the gate fidelities, and our control knob, because we want to specify, we are specifying that we want to work with time optimal things, time optimal gates, so they have to be fast. So we say that the Rabi frequency has to be the strongest possible. Then we are just left with one parameter, basically the laser phase. And so we make a piecewise constant ansatz for the laser phase. And then we maximize the fidelity as a function of, a discretization of this phase as a function of time. And then we do it until convergence to an optimal solution. So this actually works very well. You can do it yourself. And there are some problems, of course, in this case, that there are many parameters and many solutions in principle. And also there can be, if the problem is complicated, that there can be many local minimal, and the solutions may contain, may be unintelligible, and so that's not actually very good. So if you cannot really understand what's going on, that's always, sometimes it's not very satisfying, but can be the nature of the beast if you're just doing a numerical solution. We also work on a semi-analytical solution. We just flash later some results for that, but let's say that many results can be just obtained numerically if you use these kind of techniques. All right, so then how do you apply it? Well, we have indeed, we have this Rabi frequency, and then we have this complex space, this space here. And now we use effectively this symmetric type Hamiltonian with a, just coupling the two separate subspaces. This is block diagonal, and then we can get a perfect control Z gate if some condition on this initial, on this evolution of the phase is met exactly as before. Now we kind of minimize an objective function, which is the fidelity, which is 1 minus the fidelity. So we have some form for the fidelity, and then we numerically try to find the highest fidelity or the lowest possible infidelity. We start typically with random initial guesses for the form of the ansatz here. So this is the first work we did. Was basically to try to find the best possible solution for the qubit gate, which is the first element that you would have in all these kind of protocols for quantum computing. So here you see some numerical results from this first work, and you see here the infidelity, 1 minus fidelity, as a function of the duration, the maximal duration of the gate. And during this gate, we modulate the the phase of the system, of the Rabi, of the coupling, of the laser coupling. And then you see that if we take a duration too short, then the infidelity is very large. But then it starts going down, and we find a kind of a continuous line that connects essentially the lowest fidelity to the highest possible fidelity. And essentially, after a certain time scale, what we found is that you can have a perfect CZ gate using simply a modulation of the laser phase. And this is plotted here. On the left side, you have the phase as a function of time, and you have kind of this sinusoidal type shape. that, here it looks like little steps, but this is just a numerical artifact of our discretization, but we can show that, in fact, this is a continuous pulse. And this is how it looks like in the, in the block sphere. This kind of this necklace type structure for coupling to this symmetric state here. So now, what do we get out here? We get out that maybe a couple of things. So we get a gate that is just 10% maybe faster than the original one, which is therefore is very good already. The advantage is maybe that we only have a smooth manipulation or laser phase that is needed, and that maybe experimentally is not too complicated. So the advantage here is that basically you are, setting up a gate which is maybe simpler to do experimentally because yes, it uses the global addressing, but also you just have this one parameter to change. But maybe what is actually practically more useful is that if you sit here, then this is the perfect solution, the fastest, best. If you can do it, do it. But in fact, there is a lot of other solutions that look essentially, modification of deformations of this curve. And then they also give you a very high fidelity or perfect fidelity. And so in a sense, this kind of gates has to be seen as a family of gates, which is kind of forgiving a bit of how you manipulate it. And so depending on how you manipulate it, maybe you can get good results. This was just a slide to show that in fact, the solution of having a global addressing for 2 cubic gates is actually the best solution you can have. So if you have individual addressability for the 2 atoms, you don't get anything out. So actually having a global laser is a better solution. This is shown here because with individual addressing and a global laser pulse, you see that the curves are effectively exactly the same. So individual addressability brings no speed. We did the same idea also for 3 cubic gates, and so we find some solutions which basically implement a control, sorry, a C2Z gate, and actually this was optimal until you guys found that it was not. So there is even a better solution if you relax the phases even more. So well done. The idea here is you can generalize basically these pulses to have multi-qubit gates as long as they are based on this blockade mechanism. You can find pulses that achieve very high fidelity gates, and these again are very kind of forgiving pulses. There are several possibilities that give you this kind of gates. For example, here we have 2 pulses that differ almost by nothing in terms of time. They are slightly different in shapes, but they give you different population of the excited states, but give you essentially fidelity 1. And this is true for a whole family of them. And maybe that's a nice piece of this. It's really kind of forgiving for once. All right, so this was the one instead on the math side. So we spent some time thinking about whether we can do something about, beyond the purely numerical approach. Turns out you can use some variational methods, the Pontryagin maximum principal method, in this case, which basically is kind of a Lagrange approach to finding the best solution for this kind of system. If you are interested, we're very happy to discuss how to do it. So maybe what Sven found is a very nice, actually theoretically very nice way of reducing the system to just which is the problem that is a set of differential equations that can be solved very efficiently and only depend on, say, 4 variational parameters instead of a few hundred that you have to do numerically. And this is actually credit to Sven, who find a really nice analytic solution to the problem. Still, it doesn't solve the whole problem, so it still remains a variational problem but you reduces the complexity of the problem by several hundred variational things that you have to find to just 4 for cubic gates and 6 for 3 cubic gates. So through this, we are trying hard to get a better intuition. Stay tuned, maybe in a few years we get with a better intuition about these pulses, what they mean. I'm not 100% sure we'll pull it off, but we're trying hard to understand how these systems work, what they mean, these kind of gates, a bit beyond just the numerical solution. But maybe the other thing which is interesting is that, okay, so now you have basically some simple, maybe what is the scene thing is that you can have the solution of these pulses by just a few variational parameters. And then the experiments, there are now the experiments in here and also in Jeff group have shown that you can also obtain these pulses by all variation of them, which are efficiently implemented in the experiments in a kind of experimental variational way, where you kind of modulate them, you kind of on the fly until you find a high fidelity for the specific condition of the experiments. And that's maybe an advantage of this kind of approaches. Here we did it for finding the best possible. Even in the case of finding the best possible, you can reduce the problem to just a couple of differential equations which are coupled and solve those variations. Okay, so this is where we were last year. And then we started thinking about, okay, so can we go beyond this and not just have fast gates, but also approach, look at the problem of robustness. And so the kind of error sources that we started looking at are river decay, laser amplitude errors, and the tuning errors. And maybe these were, at least in some platforms, some of the dominating errors. And of course, there is work from Hannes that we will see later. But they also looked at similar problems. Our approach here is again essentially to try to look at a pulse shaping, so pulse level gates that can be implemented in this kind of systems. So what we are focusing on the next slides is to generalize the previous gate that we have seen, which is the fastest gate that you can get, to slightly slower gates, but that maybe can fight this kind of errors. So we have laser noise, quasi-static, and then also uncertainty on the detunings. There are other things that can go on in experiments, and then one has to therefore start somewhere, and maybe by solving some of these errors, one can focus now on the other errors that cannot be solved in this way, and put all the efforts there. All right, so the first error that one would like to, really fundamental error of the system, is that fundamentally these excited river states are lossy. So there is spontaneous emission on certain rate, and there, okay, that's it. Our solution was there is no solution. That's it. So the only thing you can do is go as fast as you can. That's at least the zero order one. And so the faster you can is exactly the time optimal pulse we found before. So an implementation of this gate or a very similar gate will give you the fastest possible gate you can have, and therefore you will have a reduced effect of spontaneous emission from the excited state. So the amplitude is maximal for the whole duration of the pulse, and then you just modulate the phase. Now, robustness against amplitude errors. So here, what you do is basically you have this epsilon 1, epsilon 2, which are your uncertainties, which are some small deviation that you don't know on your Rabi frequencies here. Now, what you can do, you can modify your. We have a numerical approach to this. Again, we try to find smooth pulses of your driving lasers that can maybe be robust at second order at least, or higher to these problems. So you have some. In this case, what we do, we have some objective functions that are essentially the fidelity plus something. That is some function that reduces to a perfect CZ gate if you have zero results, and is robust to respect to, in perturbation theory, basically, to small deviation of this known quantity here. So effectively, we expand in perturbation theory, and then to some order, and then we kind of plug it in, and we solve this problem numerically. So what we find then is again a class of different solutions, and this is the solution we have here. For example, for this specific case, is one again that if you crank up your Rabi frequency, so the amplitude as much as you can, and again you just modulate the phase, and the resulting phase is different from what we had before. Is some other rather forgiving continuous pulse, so there is nothing wrong with implementing this in experiments, we hope. And so it's smooth, continuous global laser pulse that also is, kind of insensitive to a certain extent to this kind of noise. And there is similar work, of course, from from Hannes and his collaborators, and also from Kokelman's group. So how does this kind of pulse actually, is it good or not to use it? Well, so here we now plot essentially, to quantify this, we can plot the infidelity as a function of the strength of the deviation of the uncertainty that one has, and first for no losses. And then what you see, this would be the time optimal pulse is the best solution if you have no deviation, but then rapidly is not robust. And so therefore, if you use this other pulse, which is only slightly longer than the original pulse, then you can get several orders of magnitude increase in sensitivity to this kind of deviations, which is good. And one can understand it because the time optimal has this dependence. Now, even in the presence of spontaneous emission, now we get kind of these expressions. And so we see that there is this dependence quadratic here. We have a loss here, which is simply the population from the excited states, and the loss from there that we had before, and okay. But then we have this epsilon 1 squared and epsilon 2 squared appearing here. While the amplitude robust one is, you lose a factor of 2, a bit less than a factor of 2 in population excited state, and therefore, in losses from spontaneous emission, but, they have a different functional dependence here. So this means that now if you plot, if you plot for realistic parameters, for example, with terbium or other system, this could be any atom, and then you see that, for small deviation, you better have the original pulse is better, but then, the losses go up, while this essentially remains insensitive overall the pulse. This was the first type of error. Another class of errors that we looked at is, Doppler shift. Now, Doppler shift is a bit more difficult in the sense that in general, you take any kind of detuning error, a general solution for detuning errors that is insensitive to lowest order, that you cannot find basically a system that converges, that gives you a perfect gate for a general situation where you have detuning of this kind. But there are situations where this can work, and an important one is Doppler shift. And here, though, the point is that you can find, while you cannot just find a pulse shaping only that solves the problem, this is a good example in which you may have to do something different. So you have to put together the pulse shaping aspects and some other tricks on the hardware side. And here, clearly, what you can do, you basically should. So the solution we propose to do is to there are at least two ways in which this problem can be solved. We can implement. What we have to do, we have to reverse the tuning. So we have to basically break up our pulse now in two pieces, so that do kind of a square root of CZ. Then reverse the tuning after this first pass half, and then reapply the tuning. And the idea basically is that we have to reverse the tuning, and then in between the two half pulses. And so there are a couple of ways in which this can be done. We call one a switch method. Simply, one would need to apply the pulse and then switch the laser direction and reapply the pulse. And or one can also, if one has a quadratic potential here, simply use the periodic atomic motion in the trap and then basically wait until the system naturally reverses the velocity. So this you have to wait in between. This is in principle not a problem because by pulse shaping you make sure that there is no readware population in the excited state, and so you can actually afford to wait. And then these are kind of the resulting pulses, and these are again not intuitive how they are done, but there is some solution that gets you precisely back in a situation where there is no population in excited state. Then you have to reverse your pulse, wait, reverse your pulse, and then do a Doppler robust. There is also solutions that can combine amplitude and Doppler robust pulses at the expenses of spending a bit more time in the excited states during the gate, and therefore also you will have more population of excited states during the gate. So you are essentially trading robustness with respect to amplitude and Doppler problem by transferring to other sources of errors. In this case is spontaneous emission from the excited states. So then you start in trading different errors. But this somehow works. Please.
Are these plots for the weight method?
What? Sorry?
Are those plots representing the weight method or also the switch method? Which operating sense?
Yeah, for both. This works for both.
Because I guess my intuition is that since for the switch method you're changing the direction of your laser K vector anyway, shouldn't it be simpler to engineer the Doppler insensitivity so your phase profile should be simpler for the switch method versus for the weight method?
I wouldn't see exactly why. That's the first thing, or maybe we can discuss later. Okay. But if you have specific ideas, we're very happy to hear them. But that'd be good. Okay, so this is the idea. We have this can be combined to avoid also tensor shifts. This can be also combined with other hardware type solutions for avoiding problems maybe from the inhomogeneity of this trap here. Can be solved by combining to other things which we are happy to discuss maybe during the break later. For example, we can modulate the trap frequency as has been demonstrated in QD experiments, and this can help solve other experimental problems. So this is kind of just an example, maybe what I want to say. This can be extended to other problems too, specific to your experimental apparatus. So, how am I doing with time? Hannes, how am I doing with time?
You have 5 more minutes and then you're...
Okay, good. So then I accelerate. Okay, so how does it work in experimental and realistic experiments? So we have taken, with Jeff, we have taken the parameters from their experiments. And now maybe just focus on this plot here. And here is the error in the amplitude, and then you have here temperature. And basically the main message here, if for this cubic gates, if you can afford to work in this, so now the dashed lines is where it's bad, some other solution is better, and the clear areas are where you find this little star is where a specific type of pulse is the best solution. So if you have very small errors and small temperatures, so if you are in this area here, your best solution is a time optimal one. And that's good to know. But if you have a larger errors, there are some pulses that are, for example, this amplitude and Doppler robust errors are, the best solution possible at higher temperatures and also larger errors. So if you are in this situation here, maybe also you have heat into your system, then if you are in this parameter range here, then you have just a single pulse that basically have a very good fidelity even for very large temperatures and other errors, and so and amplitude errors here. So in this, maybe what we want to say here is that if you work with this kind of pulses here, is much more relaxed the kind of requirements that you get for achieving a fidelity is compatible with error correction. So this I think is good news. So there are solutions that are robust also to higher temperature in realistic experimental conditions. Now, motivated by all these works that Jeff has been talking about and the community is starting working towards error correction, we looked at what happens now for logical qubits. And so this was kind of an interesting effect. I will not go through this. Jeff has explained this morning, what the experimental apparatus here. And so the idea here now that using these metastable qubits, the Ribet decay can be detected without destroying the qubit coherence. And what we find is, what they found is that there is an increased threshold for fault tolerance. And what happens now, if you look at this X code and the qubits, logical qubits for that, then these are the results you can make now. It's the same plots as before, but now for the logical qubits. And interestingly, so of course, if you are now in this error range here, again, a time optimal pulse is the best. But there are in a very large array, in very large range of parameters now, other pulses are extremely robust. So this says that you can now trade one error for another one. And in this case here, you're converting everything into essentially erasure errors. And you may win. So this maybe shows that this approach of, of very biased errors that you can convert then may actually be very interesting in the context of error correction. Because again, there are laser pulses which are extremely robust if you are able to detect now also the losses that you have. So basically, what we are saying here is that the logical error rate here can be very, very small for a large set of parameters just by utilizing these kind of techniques. And this was interesting because basically it's suggesting that you can have different strategies of optimization for physical error rates and logical error rates. And maybe this is a conceptual point that can be applied also to other systems. So in the next 20 minutes, that's what we said. In the next 2 minutes, okay, I'll now flash some results that this is a bonus for us. Okay, so this was about pulse shaping, to say that this will work with the specific hardware that everybody here is building. But if you want to build other hardware, then there are other interesting stuff that can happen. So the idea here is to look at the cavity and trapping atoms inside, and to perform local multi-qubit quantum gates in a driven cavity. So maybe just flashing the initial idea is the following. So we want as many other physical systems as spectrating qubit ions and also cavities. The idea is to derive gates via utilizing a bosonic mode as a kind of a mediator. So now you have 2 qubits here, they have light matter coupling, and then you have a bosonic mode. Okay, so there are many proposals that do that. Also from here, of course, and also experiments. And then usually the idea is that you derive, the qubits, and then the bosonic mode kind of acts as a mediator between them. So what we want to do instead here is to engineer the gates by driving simply the qubits, the bosonic mode. Don't touch the qubits, just touch the bosonic mode. The question is, can we drive gates by not looking at the qubit, but looking at the bosonic modes only? Of course, the reply is yes, okay? Because otherwise we wouldn't be explained here. We have now a pump with some strength, and that's our control. So that the system we have a bunch of atoms or molecules inside, and our goal is to drive gates by kind of pulse shaping the driving field. And this can work, in various different regimes. It works, and it works in many different regimes. So the Hamiltonian is the typical Hamiltonian you would have. You have a cavity mode, you have an atom. So you have a 3-level system, a qubit, and then some excited loss state. That is kind of, our, and then the one E transition is coupled to the cavity field. And so you have this collective coupling, in this case, or a collective spin to the bosonic mode, and then you have the pump. And we focus now on the regime of strong coupling, where when the coupling is squared, the coherent is much better than the bad stuff. There should be a parenthesis here, so which is the decay from the excited state and the decay from the cavity field. Of course, it's solved with master equation, etc., etc. So just the last slide, probably, is yes, it works. And there are various ways you can do it. What we looked at is to generate geometric gates by fast geometric gates by essentially, pulse shaping. This is the driving very strongly. So the tuning far, the delta is the tuning here between this transition here and the pump laser. This one is the tuning very far, by the same time also pump your cavity strongly in such a way that this is essentially constant. And then, so in this strong driving way, you can generate effectively a geometric gate. This works very well and gives you very fast gates, multi-qubit gates. And then you can implement CZ gates, multi-qubit CZ gates, and also GSZ, yeah, of course, GSZ states, because you implement this kind of unitaries. There is also an adiabatic version that allows you to create arbitrary phase gates by multiple application of this. Always with an infidelity scaling like n over square root of c, which is typical for, so far, for deterministic gates. And so the geometric gate is basically equivalent to a Mellmer-Sørensen solution, for which there is a very nice now analytic solution. We find an analytic solution for the Mellmer-Sørensen gate in the presence of losses, so you can get basically scalings like this. So now, and this is maybe a last slide. Okay, this is basta. I stop here. But basically, at least for the first protocol here, which is done in the regime of strong driving of the cavity, this is kind of the solution for the fidelity or for the infidelity of a CZ gate. And you see the parameters of the losses entering here. Effectively, if you optimize this, your optimal solution depends on something, and then n over square root of c, and something that depends also on n here. And this is, you can see that this kind of work. Of course, cooperativity has to be large in order to strongly benefit from this. This I will skip. These are numbers. If you're interested, we can discuss. But the reason why we're doing this is that we wanted to find ways to find alternative ways of doing error correction. Maybe if you have now these no-local gates, you can make also no-local stabilizers. And these no-local stabilizers could be quite interesting to realize LDPC type codes, which are more forgiving than the current surface codes for error correction. This is our group in Strasbourg, the theory group in Strasbourg, with Janne Schachemeier and David Dagemüller from CNRS. And this is a bunch of talented people that, if you're interested, check out what they do. They don't all do quantum computing. They also do a lot of other stuff. And this work was mainly done in collaboration with Sven, who is here. Also Vinesha for the last part, Jeff for all these works, and on error correction, and also Gavin Brennan and Macquarie University. Thank you.
Thank you, Guido, for this almost time-optimal presentation.
Almost.
Other questions? Mark.
For the gate design canceling Doppler errors, are you saying there's phase profile that's independent of temperature, or you should choose it depending on the average temperature of the atom?
No, so there are some that are really kind of independent. So as long as temperature is large enough, is independent of temperature, or for a large degree of temperatures. Yeah.
Because you had a coefficient V0 in your phase, and it's going to depend on temperature.
So like this one. So what's the question here?
Just if one should choose the phase depending on the temperature, or just
no. So this is really the same kind of shape of the pulse that is robust in all this regime here.
Can you go to where you actually defined this gate? I think Mark's question.
Yeah, right, exactly there. You have K0, V0. And so, when you have a thermal distribution, you have different velocities.
Yes, but the kind of the shape of the pulse is of this kind, basically of this kind here. I mean,
is it correct that the right axis is referring to the purple dashed line, and then the left axis is referring to the phase profile?
Exactly, yeah. So basically, all that this shows that the Doppler, that the tuning from the Doppler shift has to change sign. Has to change sign between the two pulses. And on the right side, you see the right side of this plot shows the tuning from the Doppler shift, and all that this should show that the Doppler shift should change from K0 V0 to minus K0 V0, when you can either change K or V for that. but the actual pulse shape, the pulse shape that the phase is a function of time does not depend on. It's not.
Okay. I have a half question, half comment. So first off, we really like your gates. They work very well. So then, but then here's the question, I guess related to this Doppler discussion. So we have this kind of gigantic light shift from one of our Windberg lasers, this 1013 light shift that we kind of discussed in our paper, and it's definitely one of the limitations. And like we do not currently have any pulse that we know of that is robust to this kind of detuning error, either like a pulse or some sort of other.
So this is a shift coming from X axis, a Stark shift.
Yeah, the Stark shift from this 1013 laser. And if there was an idea, it would be amazing. So
We actually discussed that in the paper. So well, we can maybe discuss it. But yeah, so I think at least for Stark shift, we have ideas how to do it. So because it turns out that they are correlated. So it gives you a detuning, but the tuning is correlated also with the amplitude. So and then this gives new solutions to the problem. So we actually discussed that in the paper, but we can let's talk about it.
But
Please.
Just to follow up on this, like like this, the tuning robustness here is specifically for Doppler, right? Like if I have a
Yeah, but we can also combine it with this other type of Stark shifts.
I see, and then it would also be robust in general to just some like random like quasi-static detuning, like kind of T2 star like effect.
So the reason why it works for a Stark shift is because it's correlated to the amplitude problem. So there is a solution there. Instead, what we show also in that the generic solution for generic detuning problem there is not. You can make it better via this. Okay, your pulse shaping you can get maybe 20% better, better fidelity, but not orders of magnitude fidelity for a generic problem. But for the specific problem that was asked, then there is a solution. So that's why one has to really go down to the specific experiment and try to find solutions which match that. That was really one of the interesting situations where actually you can find a solution.
But you're saying that, for example, for like electric fields or like random electric fields or something like that, you can't really do much just because you can't like get this. Like,
Generically, you can't, but
thank you so much.
You also think about recoil, so I think in addition to Doppler, you also get the recoil error, which I think is kind of similar in strength, but it's a different phenomenon.
So this the way which we see it is actually the solution is essentially the same. Yeah.
Because the switch method, for example, if it first consist direction and resist direction, like a pi is looking at Doppler incentives, but it would be basically the worst for a recoil, like the same in direction.
I would say that actually the problem is kind of effectively the
You
same.
come back
So,
to the ground state in between the two halves.
Yeah, then it works.
Yeah. And in fact, there's no way to do the switch without doing that. It's not sensible to say that you can do half a pulse and then the other half and have those be in phase with each other, those pulses, because that phase is not well defined. So it only makes sense to switch if you come back to the ground state. Not
This
in
one.
an array. I mean, if your array is
This
exactly
one.
commensurate with the river laser or something like that, but it can't be well defined in
Yeah,
all
you're right.
points in space.
You're right.
thank you.
No more questions. Let's thank Guido again.
Thank you.